body from a point to another against a force like spring force or gravitational force, that work gets stored as potential energy of the body. When the external force is removed, the body moves, gaining kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energies is thus conserved. Forces of this kind are called conservative forces. Coulomb force between two charges is also a conservative force. This is not surprising, since both have inverse square dependence on distance and differ mainly in the proportionality constants. The masses in the gravitational law are replaced by charges in Coulomb's law. Thus, like the potential energy of a mass in a gravitational field, we can define electrostatic potential energy of a charge in an electrostatic field. Electrostatic potential. Electrostatic potential. Let Q1, Q2, Q3 and Q4 be the unit charges. P and R is the initial and final positions. Here, work done on a test charge Q by the electrostatic field due to any given charge configuration is independent of the path and depends only on its initial and final positions. We define potential energy of a test charge Q in terms of the work done on the charge Q. This work is obviously proportional to Q, since the force at any point is QE, where E is the electric field at that point due to the given charge configuration. It is therefore convenient to divide the work by the amount of charge Q, so that the resulting quantity is independent of Q. In other words, work done per unit test charge is characteristic of the electric field associated with the charge configuration. Potential due to a point charge. Potential due to a point charge. Consider a unit positive charge QP is the point. We wish to determine the potential at P with position vector R from the origin O. For Q is greater than 0. The work done in bringing a unit positive charge from infinity to the point P against the repulsive force of charge Q is the potential at P due to the charge Q. Consider a point charge Q at the origin. For definiteness, take Q to be positive. We wish to determine the potential at any point P with position vector R from the origin. For that, we must calculate the work done in bringing a unit positive test charge from infinity to the point P. For Q is greater than 0. The work done against the repulsive force on the test charge is positive. Since work done is independent of the path, we choose a convenient path till along the radial direction from infinity to the point P. Potential due to an electric dipole. Potential due to an electric dipole. An electric dipole consists of two charges Q and minus Q separated by a small distance 2a. Its total charge is 0. It is characterized by the dipole moment vector p, whose magnitude is q into 2a. Here, r, r1 and r2 be the position vectors. These are the quantities involved in the calculation of a potential due to a dipole. An electric dipole consists of two charges, q and minus q, separated by a small distance 2a. Its total charge is 0. It is characterized by a dipole moment vector p, whose magnitude is q into 2a and which points in the direction from minus q to q. We also saw that the electric field of a dipole at a point with position vector r depends not just on the magnitude r, but also on the angle between r and p. Further, the field falls off at large distance not as 1 by r square, but as 1 by r cube. We now determine the electric potential due to a dipole and contrast it with the potential due to a single charge. Equipotential surfaces. Equipotential surface. Here, q is the single charge. The animation A represents the single charge q. The equipotential surfaces are the spherical surfaces and centered at the charge. The animation B is the electric field lines are radial. Starting from the charge if q is greater than 0. An equipotential surface is a surface with a constant value of potential at all points on the surface. Relation between field and potential. We thus arrive at two important conclusions concerning the relation between electric field and potential. Electric field is in the direction in which the potential decreases steepest. Its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point. Potential energy of a system of charges. Consider first the simple case of two charges q1 and q2 with position vector r1 and r2 relative to some origin. Let us calculate the external work done in building up this configuration. Potential energy of a system of charges. Consider the two charges q1 and q2 at the point P and R. R12 is the distance between these 2 points. Then potential energy of system of charges q1 and q2 is directly proportional to the product of charges and inversely proportional to the distance between them. This means that we consider the charges q1 and q2 initially at infinity and determine the work done by an external agency to bring the charges to the given locations. Potential energy in an external field. Potential energy of a single charge. Potential energy of a system of two charges in an external field. Potential energy of a dipole in an external field. Electrostatics of conductors. Conductors contain mobile charge carriers. In metallic conductors, these charge carriers are electrons. In a metal, the outer valence electrons part away from their atoms and are free to move. These electrons are free within the metal but not free to leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different directions. In an external electric field, they drift against the direction of the field. The positive ions, made up of the nuclei and the bound electrons, remain held in their fixed positions. In electrolytic conductors, the charge carriers are both positive and negative ions. But the situation in this case is more involved. The movement of the charge carriers is affected both by the external electric field as also by the so-called chemical forces. Inside a conductor, electrostatic field is zero. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Electric field at the surface of a charged conductor. Electrostatic shielding. Dielectrics and polarization. When a conductor is placed in an external electric field, then the free charge carriers move and charge distribution in the conductor adjusts itself in such a way that the electric field due to induced charges opposes the external field within the conductor. This happens until, in the static situation, the two fields cancel each other and the net electrostatic field in the conductor is zero. Capacitors and capacitance. A capacitor is a system of two conductors separated by an insulator. The conductors have charges, say Q1 and Q2, and potentials V1 and V2. Usually, in practice, the two conductors have charges Q and minus Q with potential difference V is equal to V1 minus V2 between them. The parallel plate capacitor. A parallel plate capacitor consists of two large plane parallel conducting plates separated by a small distance. We first take the intervening medium between the plates to be vacuum. The parallel plate capacitor. A parallel plate capacitor consists of two large plane parallel conducting plates separated by small distance. Let A be the area of each plate and D is the separation between them. The two plates have charges Q and minus Q. Sigma and minus sigma is the surface charge density of plates 1 and 2 respectively. Effect of dielectric on capacitance combination of capacitors. We can combine several capacitors of capacitance C1, C2 and so on till Cn to obtain a system with some effective capacitance C. The effective capacitance depends on the way the individual capacitors are combined. There are two simple possibilities: capacitors in series and capacitors in parallel. Energy stored in a capacitor. A capacitor is a system of two conductors with charge Q and minus Q. To determine the energy stored in this configuration, consider initially two uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1 bit by bit, so that at the end conductor 1 gets charge Q. By charge conservation, conductor 2 has charge minus Q at the end. Van de Graaff generator. Van de Graaff generator. The Van de Graaff generator is the machine that can build up high voltage of a few million volts. The resulting large electric fields are used to accelerate charged particles to high energies needed for experiments to probe the small-scale structure of the matter. Working. In this Van de Graaff generator, a large spherical conducting shell is supported at a height several meters above the ground on an insulating column. A long, narrow, endless belt, insulating material like rubber or silk, is wound around two pulleys, one at ground level, one at the center of the shell. This belt is kept continuously moving by a motor driving the lower pulley. It continuously carries positive charge sprayed onto it by a brush at ground level to the top. There it transfers its positive charge to another conducting brush connected to the large shell. Thus, positive charge is transferred to the shell, where it spreads out uniformly on the outer surface. In this way, voltage difference of volts with respect to ground can be built up. This is a machine that can build up high voltages of the order of a few million volts. The resulting large electric fields are used to accelerate charged particles, electrons, protons, ions, to high energies needed for experiments to probe the small-scale structure of matter.